Recording.
Once again here we're looking at the binary resonant system with L1, C1 on the left, C2, L2 on the right, and then we're going to put a rectification or load across this midpoint path. Now currently we're at 3.6 volts. Let me turn the light on here. Having problems with our headlights, blind light. Presently we got 3.5 volts, enabling almost an amp, 0.95 amps into the system. That 0.95 amps splits into two coil deliveries. The back coil, 0.56 amps, which has no inductive loading, and the front coil, which has 0.47 amps, which furthermore situates on top a conical high induction coil and a special secondary relationship here that we wish to further show. This is the plug that would enable this system to work if it was line driven. In this situation, because the system is obtaining all of its power through the air through one of these coils, then we see that to show the differences in how the bottom coil system will respond as a dual coil system versus what would be expected as a single coil system, when we in fact do have the short across the plug. We'll have to go back over here and look at our metering and look at this meter here, the front meter. The front meter is showing 12.7 milliamps and the back coil meter is showing practically nothing. Okay, now what we also have on opposite to this shorted plug is we have a neon load. And to give the great understanding here of why we've arranged things this way, we can watch what happens then when we simply remove the shorted plug. The former 190 volts is reduced to 8 volts. So we can see that there's some peculiarities on the system, but now more importantly, now there is no place for the current, induced current to go on this coil. We've just removed its short path. The consequence of that short path being removed is now it's taken the entire other back coil system as that short path, and we have 7.3 milliamps on each coil in that situation and 7 volts across the load. And then we got a hamster down there. We have on 197 volts there in this orientation. Now going back over to here, our concern here is to show, forgot to set the clock. We want to go to now we want to increase the range here and show the action of the circuit, the main circuit. We got 3.6 amps input in that 1 amp, split between those two divisions. Now on the input AC volts to rectifier, we have 7.8 volts, roughly double or so what the input volts are. And then down here we got 0.18 amps going through the rectification system, and we got a DC cell voltage pulsed at 0.16 amps and only 8 volts. And our cell down here is 4 concentric cells in series, so we haven't got high enough to really make any appreciable amperage. Now we're going to go over here and turn up the input process so that we can get some appreciable amperage. Ah, kitty. And well, we want to go up probably to equalize that. I recall is 11.3 volts. We're at 9. Go over there, Jim. We're at 11.8. Now we can see that at 11.2 volts, our voltages are equal. In that case, we assume this is declared the maximum energy transfer of the circuit. We have 11.2 volts going in, taking 1.44 amps Then we got 11.4 volts going to the rectification system. Coming down here and only allowing 0.75 amps through at 10.47 volts. Now we're going to double that again. Now we're going to go back to the secondary system and look at the secondary system. Now we got 378 volts across that bulb for an 11 volt input. And what we're going to do then is increase the voltage to the limits of that 750 volts of that meter so we can get the neon bulb to load. And then of course we want to watch that meter so we don't exceed the 750 volts. It's pretty borderline there when it will light. Okay, now once we've lit, we got a fairly constant repetition rate. We can see now the back coil is receiving more amperage proportionally than what it used to. We tone that up just a hair more. Don't like to have voltage meters. Our voltage across the bulb is a flickering 300 volts now. Now going back to the main system here. We now have 29.6 volts, enabling 2.2 amps, and 1.9 and 2, we got more amperage circulating on the sides than what we're inputting, so we're in tank circuit operation. And then our output at this stage then is 2.65 amps going in from a 15 volt source, translating down to almost 13 volts at 2.3 amps. And maybe if the camera can see there, there's the action of the cell with that 2 amps. Now what we're going to try to do quickly and finish up here is we're going to replace that solution with distilled water and look at our new power transfer point.